Hi, it's Greg Magnan from Seattle U with our fourth entry into our series of managing inventory. Inventory control, the reorder point. This video is about when to reorder. At what point of your inventory levels should you place an order so the rest of what you have on hand will last you until that order arrives. That's what we're talking about today. It's part of our set of decisions that we make around inventory management. Previously, we've seen this slide. This time we're talking about the very top. When should an order be placed to replenish? When should you buy more gas? Do you wait till your gas light comes on? Some of you are a little more risk takers. You might say, oh, my gas light's on. That means I have 2 more gallons. I might have another 60 miles to go. I'm going to find the cheapest gas I can within that 60-mile window. Some of you are perhaps more risk averse than that. You never want to see this light come on. Your reorder point is much higher than 2 gallons left in the tank. That's too close to empty. And some of you might even think like, I don't let my gas tank get below half because I think I get worse gas mileage if that happens. I'm pretty sure that's been debunked, but you can manage your gas level how you like. That's just an example. So here we go. So here's our problem. It's the same one we worked on in the EOQ video. We have a distributor that's buying filters from a supplier for $50 each. It's a 52-week year. Pure demand was 60 per week, so that was 3120 for annual demand, 3,120. Ordering costs 60. Holding costs 30%. We had that 30% times the $50 product cost for a $15 per year holding. And in this case, we're going to have some other variables come into play, and we'll talk about these in a second: the service level and lead time and standard deviation of demand. Remember, we talked about variability a couple of videos ago. This is why inventory exists, because of variation. So here's our challenge. This has been the same objective all the way through: minimize our costs related to ordering, related to holding, and in this case, we also want to meet our service level obligations. So this video and the ROP calculation is part of the R of the QR inventory policy. And at the bottom here, it says we're going to reorder when our current inventory reaches some trigger level, some amount. And what we're dealing with is variability in demand, and then variability in supply, and variability in lead time. So the reorder point seeks to minimize our costs and meet service level objectives. So I've grayed out the variables that only pertain to EOQ, and I've kept in the ones that we are going to need. So we're going to look at this from a deterministic standpoint first. Let me go back to this other side. Here we're talking about variation in demand, variation in supplier lead time. Let's imagine this problem without variation. That's our deterministic scenario. The future is determined and known and constant and fixed. So what does that mean? That means that we should order when we're going to run out of inventory, and then the products are going to show up. So in this case, demand during lead time, demand is 30 units or 60 units, per week, and lead time is 2 weeks. So that means we should order when we get to 120, and then as soon as we sell our last filter, boom, here comes the truck and the delivery driver bringing our new batch. Right away we get replenished about what we need, because we can do that because everything is fixed and known. As you are likely aware, life doesn't happen that way. So the stuff that I'm graying out here, because that's the deterministic model, is not going to be grayed out. So in the deterministic scenario, we know demand, we know lead time, there is no risk, there's no variability. So in this case, order when you get to 120. Except life happens. So here's what that deterministic scenario looks like. We're going to order when we get to 120. So we started at 120. We started with more than 120. We are going to order when we get to 120. A week goes by, we sell 60. A week goes by, we sell 60 more. Then we get some in stock. We start to burn it down. We get to 120. A week goes by, we sell 60. And as soon as we sell that one there, the truck arrives, etc. A little bit simple, more simple than we're dealing with. So there's the The reorder point is when our inventory level crosses whatever that predetermined ROP line, reorder point line is. And then the lead time is from when we place the order to when we receive. In our example here, in our deterministic example, the lead time is known to be 2 weeks exactly, and then it shows up. Never late, never early, exactly 2 weeks. And then we receive the queue. So here's this notion of demand during lead time. We place the order, and then we receive the order. So the lead time is between those two. Demand during lead time is what we're focused on there. So let's open it up to real life. Let's have a stochastic scenario where we have variability. There's variability in demand. There's variability in supply. We still need to meet our service promises to customers. We still need to keep our factory running if we're buying stuff. We still need to keep our pantries stocked, etc. So in this case, from our problem, we need one more piece of information, the standard deviation of weekly demand. So demand is variable. It can change each week. So here's our independent demand. It's stochastic. So rather than straight lines in between, we have a little bit of a wavy line, and then we receive, right? So our same things apply. Lead time is happening. We're receiving orders. We're placing orders. We still have demand during lead time, except demand during lead time is not a straight line anymore. Something else might be able to happen. So let's zoom in a little bit on that. And after we place the order, right here is when we place the order. Demand can be the same, it can be slower, it can be fast. This is a slower demand rate here, even slower, and then maybe it's a faster demand rate than we're used to. So we need to account for the fact sometimes demand is going to be faster. And if you notice here, we stack out before the order comes in, right? So we might want to say, you know what, I don't want that to happen. Sometimes demand is greater than average. I want to be ready for it. That's our cycle service level that we looked at in the first video. All right, so to answer this question, well, when should we reorder? And we want to account for the occasions when demand is greater than we thought it was going to be. We also want to account for occasions when, well, the lead time was supposed to be 2 weeks, but maybe it got stretched out, right? And this line moves over to the right. So now we're not going to get our order for 3 more days, and we need to account for that as well. So we need to use the standard normal curve, the unit curve, that you've seen in your statistics classes. And we want to calculate this level of variability. So we're going to have, if we have this much inventory, the yellow area, we're leaving some uncovered. So we're going to have some likelihood of a stock out. And this is going to be related to that cycle service level. This is a policy decision from the organization's perspective. It might be set by the inventory manager, the materials manager, supply chain person, or in finished goods situation, it might be supplied by the marketing manager. It's part of our value proposition. Remember, delivery reliability is a thing, and we need to have product in stock if we're going to be related to that. So in the middle of this is our average demand, but where you want, and if demand is slower than average or we get delivered faster, we're covered, right? We're mostly interested here in covering our stockouts, meeting our service level obligations. So if things happen in our favor, guess what? We're meeting our service level obligations. It's when they're not in our favor that it's a problem. Demand is greater than usual and supply takes longer than usual. That's when we're vulnerable. That's when we're at risk. So you see this notion again, right? Here's our normal sweet spot level. Sometimes it's slower, the green dot, sometimes it's the red dot, and we are somewhat in trouble. So demand during lead time can be greater than we normally think. So here's our overall equation. There are other equations in textbooks and online to calculate reorder point. There are different ways to get there. We're using this way. If you need to learn a different way, then you'll need to find a different source for that information. So demand during lead time plus safety stock. Let me go up to back to these equations. Right here, demand during lead time plus safety stock is what we're working at. So demand during lead time is always there. Then safety stock is going to be the just in case of variability in demand and variability in supply. So demand during lead time plus just in case. So this whole thing from Z all the way through multiplied by that square root is the just in case. So in our case, demand during lead time is the same thing. Lead time's 2 weeks, demand is 60 per week, demand during lead time is 120. Plus just in case. Just in case what? Just in case demand is greater than usual, just in case supply takes longer than usual. So in this case, the company had a cycle service level policy to be in stock 80% of the time. So that means not 100%, but they said, yeah, 80% will be good enough. That means 20% of the time they're willing to be out of stock, taking a risk, and maybe it affects the cost of a stock out, and maybe affects their brand, maybe that customer is frustrated, or maybe not. And there you have decided 80% is the right number. So let's take a look at the rest of this formula. Under the square root is the average lead time. So the line over the top means average lead time multiplied by the variance of demand. So this is the standard deviation sign squared. That equals the variance, and the little d is the variance of period demand. In our case, it's going to be weekly. So we multiply these two together, average lead time and the variance of demand, plus the average demand squared times the variance of lead time. So it's a little bit confusing. When you're doing this problem, make sure you're getting things right. Notice that this is a multiplication sign, this is a multiplication sign, and this is addition. I have a note over here, pay attention to the order of operations. We multiply before we add. Multiply these two together, then multiply these two together, then add them together, then take the square root. First do the multiplication, then do the addition, then do the square root. That's the order of operations. So pay attention to that. Pay attention to make sure if you're giving standard deviation numbers, that you have to square them to get the variance, right? In our case, we were. So and we'll get to the 84 here in a second, but let's look at the rest of these. Lead time is 2 weeks. The standard deviation of demand was 10, so we need to square that. Average lead time, average demand is 60 units per week, per time period. So we're going to square that, and we're going to multiply that by the variance of lead time. In our problem, we didn't have any the variance of lead time was 0, so we need to add it in here. If you see a problem where there is a standard deviation of lead time, then you would put that in to represent your lead time and then square that to get to a variance. So in this case, it says we do that whole calculation, it's an extra 12 units. So our new reorder point becomes 132. It's the 120 plus 12 for just in case. Just in case what? Demand is greater or supply takes longer. That's what we're protecting against. So this z-score, remember our cycle service level policy was 80%. So find yourself a z-table, look online, look in your books, look wherever you have a z-table somewhere. And we are trying to find 0.8, because we're trying to find what's the z-value that covers 80% of the area under that standard normal curve. So find something close to 0.8, that's this number here, and then to get the z-score, we go over to the left for the tenths place and straight up for the hundredths. So in this case, it's 0.84, and in fact, yes, that's the number we have in here. Why do we have that? Because the cycle service level policy was 80%. What if the cycle service level policy was 90%? We would find the 90, that lives right around here, and it would be 1.28. 95 would be right around here, and that would be 1.64. You could also use 1.65, that would work as well, right? So you're finding the cycle service level percentage, the policy rate inside of the body of the table, and then you're going out to get the Z calculations. And again, there's our 0.84. So here's our overall solution. Remember from the previous video of how much to order, our EOQ said to order 158 units when we do, and that balanced out holding costs and ordering costs given the numbers of the problem. And then our policy overall then will be, okay, when you get to 132, place an order. It takes about 2 weeks plus or minus. In fact, for us, it takes exactly 2 weeks. The the standard deviation of demand was, or lead time was 0. But sometimes demand can be greater, sometimes smaller, and then we get 158. Time goes by, we get to 150 or 132 units left. Let's place an order. And again, sometimes when demand is greater, we'll dip into the safety stock. In this image here, we're not at that point. We're not at that point yet. You could ask the question, well, what if the company wanted to have a cycle service level of 95%? What if they wanted to have better service for their customers? In this case, we did the lookup to get to 1.65 from the Z table, from the standard normal table, which is saying we are going to go over 1.65 standard deviations. That's what this number means. Z, if we had units of Z, the units are number of standard deviations over from the mean. In the 80% scenario, it said go over 0.84 standard deviations. In the 95% scenario, it's going to say go over 1.64 standard deviations to get coverage. So this Z becomes 1.64, 1.65. Everything else is the same. So what changed now are, this is the only number different. The 14.14 was the same, the 120 is the same, but now we're multiplying it by 1.65. So our safety stock now is actually 23 units. So but it's only 11 more than the previous. So the question says, what happens if service went from 80 to 95? How much more would that cost? And the answer is, well, 11 more units, because it was 132 at 80%. The reorder point now is 143, right? So the reorder point's going up by some. That's going to raise our average inventory by 11 units. Well, how much does it cost to carry 1 unit for 1 year? $15. 11 times 15 equals 165. We could also be asking some other what ifs. So what if we wanted to raise our service level but not incur extra costs? What might we do? One thing we could do is look at lead times. We have control over lead times. If we made lead time only 1 week, the reorder point goes down. If we reduce the standard deviation of demand, then things could go down. If we improve the standard deviation of lead time, right? So we could reduce the average lead time and maybe the variance of lead time. All those would help us lower the reorder point that might offset this number going from 0.84 to 1.65, from 80% to 95. That's the end of our series of inventory videos from what is inventory about, decisions and different demand types, independent and dependent demand. And by the way, both of these have been around dependent demand. Independent demand is the MRP video that will be coming up. So it's not, I guess, not the end of all of our inventory videos, but these ones about when and how much in an independent demand scenario. Thanks for watching.